Uh, so good afternoon once again, everyone. So welcome you all in the lecture 12. So this lecture will be delivered by our eminent speaker, Dr. Soradeep Day. So before he will start his lecture, I want to introduce him. So Dr. Soradeep Day has received his BTech degree in electrical engineering from West Bengal University of Technology. Maulana Abdul Kalam Azad University of Technology, Kolkata, India in 2013. He received his MA degree in electrical engineering from Indian Institute of Engineering, Science and Technology, Sirpur, India in 2015. And he received his PhD degree in electrical engineering department from Indian Institute of Technology, Kanpur, India in 2023. He is currently working as an assistant professor in electrical engineering department, Motilal Nehru National Institute of Technology, Allahabad. His research interests focused on cooperative control, time delayed system and switched systems. So now over to our eminent speaker, Dr. Soradeep Dey. Yes, sir.
Thank you, Dr. Prajapati, for introducing me. So today we'll discuss on introduction to time-period cyber physical systems and stability framework. So till now you have been familiar with what is cyber physical systems, and today we'll mostly investigate our time for the analysis of time delays in the system. So how delays affect your system stability and how to mitigate the effect of delay or to prove that your system will be stable even if the delays are present in your system. So basically, I will go for a tracking problem to say what should be the effect of these delays in case of your CPS, and we'll show that how bounded tracking will be possible via some control estimator based architecture. And in general, these delays will have destabilizing effect in your system. So we'll consider a particular vehicle system, a multi-vehicle system, and there we'll check that if these delays are present in your system, so your protocols should be able to handle those kind of delays, and at the same time, they should have significant amount of performance in your MS. So this is a pictorial diagram of your CPS. So the design domain for cyber physical systems is this. These CPS are designed at the intersection of computing, control, and communication. The computing part includes things like microcontrollers, real-time operating systems, FPGAs, and these flash memories, and converters like your ADC or DAC, which are commonly used in embedded systems. And since these CPS often use sensor networks and communication between the processors, networking tools are important. The control part involves different control techniques, DSP algorithms, and real-time control methods. And most importantly, CPS are also spread across multiple systems requiring knowledge of distributed computing and control. So today we'll mostly discuss on this distributed control and how the delays will be there in the system. So these delays are actually unavoidable in your system, and how to design the design space for that. So we'll take a tracking problem. So before going to the tracking problem, let me introduce what is consensus. So consensus means as if in general agreement among a group of agents such that they interact with each other in a distributed manner and finally converge to some of the decision variable. Now that decision variable can be position, that decision can be velocity, So it depends on the user's choice. Now we'll go for tracking. So in that particular case, I am having a dynamic leader in my system, and the objective is that all the vehicles will finally follow this particular leader. So this is an example of cooperative guidance in multi-mission network where there is a group of followers and the task is to follow the leader. So in this particular CPS system, where delays can arise, because we want that these followers will finally track this leader with the importance of communication among different followers. So information exchange takes place between the followers, and that involves a delay due to the limitation of your communication bandwidth. And also these delays have some processing also. So due to the processing of the actuators of these agents or vehicles, there will be input delays also present in the system. So our objective is to design a distributed control log. So distributed means that the neighboring, so I am one agent and I am having the information of the neighboring agents. So based on that, I have to track a virtual leader. And to solve this, the best way is to represent the communication topology in terms of a graph, and this is kind of a necessary and sufficient condition for achieving the tracking. That is, this graph will contain a rooted directed spanning tree. Mathematically, what does it mean? That Laplacian matrix corresponding to that particular graph will have a simple eigenvalue at origin. So actually, the presence of this simple eigenvalue or origin will ensure that consensus will be achieved. If this condition is violated, then you cannot guarantee consensus. So this is the basic requirement, even if delays are present in your system or in the absence of your delays. Now, delays will come into your system. So as we are discussing that there are two kinds of delays. One is because of the limitation of the bandwidth of your communication channel, which we normally call as communication delays. And another is input delays, which arise due to the delays in your actuation system. Now, what will happen whenever you are having this group of agents working together, then these two kind of delays interact with each other and they have mixed effect on your system. So normally these delays will deteriorate the performance of the system and may lead to instability. And the problem becomes more complex when they have the interaction of each other, because input delays will have some effect, particularly communication delays will affect in some other way. Now it is, if it is somehow possible that we can segregate the effect of these two kind of delays, then the problem will be easier to solve. So for this CPS, we'll consider that the agents have the double integrated dynamics. And of course, we assume that my communication graph along with the desired trajectory has a rooted directed spanning tree. So normally this communication graph has this node set V and edge sets E, and an edge of this graph will be denoted as IK if node K receives information from node I. So now let's say you are having that n number of nodes, then you can actually find what should be my adjacency matrix. So edge weights are positive if the edge exists in the system, and if there is no edge in the graph, in that particular case, we will assign that to be 0. That means there is no information flow. So this is basically the mathematical representation of the graph. So here N represents the number of vehicles present in your system. And we have this N plus one number of agents. Why? Because the reference trajectory or the desired trajectory that we can consider as a virtual agent. So I am having a number of agents in my system and one virtual agent. So the total number of agents becomes n plus 1. Now my Laplacian matrix will be in terms of n plus 1 number of agents. And based on our assumption, so our assumption was that my graph will have a rooted directed spanning tree. Based on this assumption, you can actually find this suitable kind of mathematical representation of the Laplacian matrix. So it has two parts. The first one is this ln plus b, and this is the zero value. And what is this vector bn? That represents that the information of desired trajectory is coming to some agents. If it is coming to some agents, then the values will be greater than 0. And if the information is not coming, I mean that agent doesn't have the information of the desired trajectory, particularly that particular agent will be exactly 0. And one nice property exists is that ln plus b matrix will have all the eigenvalues in the right half complex plane, in the open right half complex plane. So the problem is I have to develop a control protocol such that these n number of agents. So for this particular CPS, we have considered double integrated dynamics. So this n number of agents will follow a general trajectory. And the thing is that this general trajectory or the reference trajectory is not fully known to all agents. And delays are two kinds of delays are present in your system. One is communication delay, which is more significant in case of your CPS. And also due to the processing of my agents, there are input delays are also present, and these are heterogeneous in nature. So we'll go for a dual layered architecture where an estimator will be there to for the desired trajectory, and there will be a tracking controller. So we'll go in details. What does it mean? Normally, this estimator-based controller architecture will help you in segregating the kind of delays. If you don't have this estimator-based controller, then there will be mixed effect of delays, which we want to avoid in my system. So, okay, one more thing is that as the number of communication links is grow on increasing, then what will happen? Your delay margin is normally goes on decreasing. So what is delay margin? That means, let's say I am having a delay margin of D. That means I can handle up to D value of delays in my system. If the delay value is greater than D, then my system will be unstable. And if the value of delay is less than D, then my system will be stable. So that dictates that margin of my system, margin based on the instability. So if you increase the number of communication links, then this delay margin is less. So our approach will be that to make the delay margin as high as possible. So we'll go for some simpler kind of communication topology such that I can have smallest number of links. Now for this, I am having, let's say, estimate of agent type follows desired trajectory if available. And if the information of this desired trajectory is not available, then estimate of agent I will follow the next agent, that is agent I plus 1 modulo n. So in this particular case, we have considered, let's say, this tau I com to be the delay due to information flow from I plus 1th agent to ith agent. So we have taken a simple graph. The agent will have, so I am having this ith agent, so the information flow will become I plus 1th agent only. Now, the thing is that if I having this particular, let's say, graph structure, then how to solve this tracking problem. Now, let me introduce the tracking problem in a more mathematical way. So, yeah, we have taken first this assumption that the acceleration of the digit trajectory, that is xt double dot t, that is available to all agents. And in the presence of this tau I com and the tau I in, that is the input delay of, let's say, ith agent and communication delay of ith agent, such that for any initial configuration of agents, the position tracking error and the velocity tracking error will be uniformly ultimately bounded. What does it mean? That agents can start from any position in the RN plane, and you have to develop a controller such that they will finally converge to the desired trajectory. Now, why this is coming as ultimately bounded? Because I am having this input delay present in my system. So if I am having the input delay present in my system, for the exact tracking, I will require the information of xt double dot t plus some value. That means the future value of the acceleration of your desired trajectory. But the future value of acceleration of trajectory is practically not possible. So at most what we can have the present value of the acceleration of your desired trajectory. So in that particular case, of course, all the vehicles will try to follow that desired trajectory. However, based on what is that particular value of input in a new system, they will have little bit difference. Now, mathematically, we talk that this should be uniformly ultimately bounded, and this thing can be established through the Lyapunov theory. This is the formal definition of UUV in case of time delayed system. So, uh, compared to your ordinary differential equation, now you will have a retarded functional differential equation, because in this particular case, not only based on the current state of the agents, but on the past history of the agents, the evolution of the agents will be occurring. So that's why in this particular case, if you see here xt theta, that represents the first value, because here this theta varies from minus tau to 0. Now, the solution of the xt of these systems will be uniformly ultimately bounded if there exists a beta greater than 0, such that for any alpha greater than 0, there will exist a time t, which will be a function of alpha, will be greater than 0, such that my solution, the absolute value of my solution, must be less than equal to beta. So yeah, it's quite mathematical. So let it make it easy that, let's say, the error between the desired trajectory and the actual agent states will always be bounded in nature, and we have to prove that. So how to do that? So as we have told that I will have a tracking controller part and a estimator part, right? So what is the function of this tracking controller? So in this particular case, you just see here, this is my agent dynamics. So this involves this delay of tau I in, xit is the position, vit is the velocity of ith agent. Now, in this particular case, there will be no communication. So in this particular case, let's say xi hat and vi hat are the representation of the desired trajectory. So let's say xi hat is, let's say, is the desired position, vi hat is the desired velocity, and I have to design a control architecture such that xit converts to xi hat, vit converts to vi hat. That is the objective. That's why this is decentralized tracking controller, because there is no distributed control is happening here. That will happen in my estimate structure. So simply what we will do, we will take the difference between xit and xi hat and vit and vi hat, and this kip and kip are the constants. So we can suitably design what should be the value of kip and kip such that my tracking controller will be stable. So based on the relative error of the position and the velocity, I can formulate what should be the correcting signal here. And what is that vi hat dot t? That is kind of a representation of, let's say, xd dot. So finally, what I want that xit should be xi hat t and vit should be vi hat t. Now, from where this xi hat t and vi hat t are coming, that will be clear when we go for the distributed estimator dynamics. Now, why this is distributed estimator? Because in this particular case, we are taking the information from the neighboring agents. Now, in this particular case, we have written only xi plus 1 hat. Why? Because in our simplest graph structure, I am considering that information is coming from I plus 1 agent to I agent, because we want that my communication link should be as low as possible. So this is the xi plus 1 hat t that is coming from I plus 1th agent, and this is the velocity of I plus 1th agent estimated state. Now there will be a communication delay. So this is my delayed value of my position, estimated position of I plus 1th agent, and same for the velocity also. What we are doing in this particular case, this xi hat t is the estimated state of the present agent, but intentionally we will delay this state by the same magnitude time y component. Okay. So intentionally we are taking the delayed value of own state, and here due to the practical consideration, the delayed value of neighboring agent states are coming into the system. Now we are taking the CIP and CIV again are constant, and we have to design the value of CIP and CIV. So these are of course greater than 0, this CIP and CIV, and it will have some upper bound. Now this corrective action will come here, and xt double dot t is the desired value of your acceleration, desired acceleration of your reference trajectory. Based on that, I can make sure that xi hat t should converge to, let's say, xdt, and vi hat t should converge to xd dot t. Now, how to do that? For that, okay. Before that, this estimator dynamics is there if my agent has no information on the desired trajectory. But if my agent, let's say, has the information of desired trajectory, then we will directly take this xdt and xd dot t. And it becomes, of course, simpler for the agent who has the information of this xdt and xd dot t. So now I have to make sure what should be my, this is my agent dynamics double integrated agents, and I have to, let's say, ensure bounded traffic. So whatever we have seen in the block diagram, this is just a mathematical representation. So here we are taking the relative difference between the velocity of neighboring agents, of course, relative position of the neighboring agents, and we, let's say, have designed this kind of estimate. And generally, we can take the initial estimates of each agent are 0. Even if you are taking some garbage value, then also it will work. But let's say we are taking that to be 0 only, and we want to ensure bounded tracking in my system. One thing you should know here, that in my control input, I am not taking x double dot t, though it is known to me. Because by taking this vi hat dot t instead of this xt double dot t leads to a decoupling among the individual agents in terms of the condition on control gains and input delays required to ensure bounded traffic. So this is just for the easiness of solving, where we want to segregate the effect of delays. Now, let's say we are defining the error variables like this. This is my desired trajectory. This is the estimate of the desired trajectory. Same for the velocity state also. And what about these two states? This is the difference between actual agent states and the estimated states. So you just see here, if these error variables goes to 0, then finally xit will be equal to, let's say, xi hat t at time t tends to infinity, and xi hat t is, let's say, towards xdt, then finally xit will be equal to xdt. Similarly, for the vit will be x dot. That is the objective. So exactly we can do that because we don't have the future information of the trajectory acceleration. So of course there will be little bit deviation between xit and xdt, but that should be bounded in nature. So here this delta estimated states, suppose we are trying to find out based on the first two error variables. And we can say that the estimator will be stable or the error of the estimator will decay to 0 if we can prove that these characteristics polynomial have negative real parts roots. So uh, this will come after computation of your retarded differential equation. From there, you can convert to Laplace transform. You can get the characteristics polynomial, and at the end, this is the characteristics equation of your system. Now you just see when AID equal to 1, that means the information of the trajectory is particularly coming to ith agent. Then we just have to ensure that these particular factor have negative real parts. The roots of this will have to have negative real parts. That is just possible for positive values gamma IV and gamma IV. But when the information of the trajectory is not coming to ith agent, that time I have to ensure that this particular factor will have negative real parts. And after calculation, you can found that if your communication delay is bounded by this particular term, then your estimator will be stable. So this is the margin on your communication delay. So that is for the estimator aerodynamics. Similarly, we have to do for the tracking aerodynamics. So for the tracking aerodynamics, if you rearrange the equation, you will finally come to this kind of retarded functional differential equation. So whenever you are having this kind of equation and you have to prove the EUP, then to solve that, we can go for several methods like Lyapunov-Krasovsky method, Lyapunov-Razumikin method, where actually the intention is that the energy of the systems will gradually decay. So different from your only Lyapunov function, so this is the energy of the function, I have to now consider the effect of the past values also. So that's why these integral terms are coming in your Lyapunov-Krasovsky candidate. So I have to consider the energy of the past states also. In that particular way, we can ensure stability of time delayed system. So the basic idea is similar. If this is your Lyapunov function, now you have to make sure that Vi dot should be less than equal to, let's say, 0. So then the energy should gradually decrease. So in this particular case, after derivation, you just see here, this P1I, QI, and SI. These matrices are positive definite matrices. Why? Because I want that energy to be positive. So this matrices should be positive definite. This should be positive definite, and this matrix should be positive definite. And I have to satisfy this Wi. These are the plus k infinity function. So after mathematical derivation, that is a long process, so I'm not going through the derivation. You can finally end up of finding the feasibility of existence of this particular linear matrix inequality. So this kind of linear matrix inequality will come in your system, and if this matrix inequality is giving feasible solution, then you are done. That means you are ensuring bounded stability. So in this particular case, we can use, so there are so many MATLAB packages are also available in your system. You can go for the semi-definite programming. There is L09 toolbox also present in the package is available in the MATLAB. by which you can solve this kind of dilemma. So let's say your tracking error is also stable, your estimator dynamics is also stable. In that particular case, we can prove that difference between the XD and XI, and here also XD dot and PI are going to be uniformly ultimately found. So that is one kind of estimator structure we have shown. Now let's explore different kind of estimator structure. So actually the estimator structure will take care of your communication delays in your system. Now you can come up with some novel kind of estimator structure also by which you can make the delay margin of your system as high as possible. Because if your estimator structure is something like that, it can yield better delay margin, then in the terms of the CPS time delay stability, it is appreciated. Of course, performance is also an important criteria whenever you will look into this. So there exists a trade-off between this performance and what kind of estimated structure you are going to use. So the previous one was like double integrated estimated structure. If I just go here, then we just see here in the estimator structure, we had xi hat dot t equal to vi hat t, and vi hat dot t equals to the other terms, the relative error compensation terms are present in the system. Here, what we are doing, simply we are having here, let's say this is one single integrated estimator, this is another single integrated estimator. So that's why they are coupled single integrated estimator structure. And whenever we are having this xi hat dot t, then we take the correction terms in terms of position. And whenever we are having this vi hat dot t, then we are taking the relative difference terms of the velocities of the neighboring agents. So that is the way of difference. Like for the position correction term, you are calculating for the neighboring agents positions, and for the evaluation of your estimator of the velocity, you are taking the relative difference of the velocity estimates of the other agents, neighboring agents. And the rest is same. I am having that same graph. So that AID equal to 1 means that agent I has the knowledge of XT, and AID equal to 0 means I don't have the value of the desired trajectory. So same you can find from this determinate differential equation. You can have the Laplace transform, and after that you can find what should be the characteristics polynomial, and from that you can find what should be the delay margin. And in this particular case, you can see that delay margin is given by this particular quantity. Okay. And this delay margin was for the previous case. So that is the difference. Tracking controller, that is same for both the design, that is design 1 and design 2, and that will be feasible if this LMI has a feasible solution. So while we have, so whenever we are going for these two kind of designs of the estimators, now it is important to analyze which one yield better delay margin. So let's say FI1 is the delay margin for design 1. So this value we are telling that say this is FI1, that is the delay margin based on the estimated design 1. And this is FI2, that is the communication delay margin based on the estimator of design 2. So theoretically, you can prove that this shaded region, that yellow color region, in this particular case, FI2 is greater than FI1. So whenever I am having this coupled single integrated estimator structure, that will yield better delay margin compared to the double integrated estimator structure. So what is that condition? That is either CIP should be less than equal to CIP, so this region, or CIP less than equal to pi by 2. So this is this region. So this is sufficient condition such that your second integrated estimator yields better delay margin. So is it like that? Then always we go for the second, the design two, that is the coupled integrated based estimator sector. For that, I have to exactly find what should be the segregation region, and that can be done using numerical methods. So here you can see that suppose for a given CIP greater than, so why we are taking CIP greater than pi by 2? Because we now want to have, because in this particular region we have to do that Fi2 is greater than Fi1. So the remaining portion left is the white one, which is not unshaded region. So in this particular region, our objective is that on which spaces that delay margin of design 1 will be greater than design 2. For that, you will finally solve, you will get one particular CIP equal to CIP star. So graphically, you can see, let's say at this particular positions at CIP equal to CIP star, you are having both the delay margin to be same. So that will represent that both the estimator structure have the same delay margin around this curve. And the green shaded region means your design 2 will be better, and the blue shaded region means the green shaded region means design 1 is better, and blue shaded region means that design 2 will be better. So it depends on what are the possible values of your delays in your system. Based on that, you can choose which estimator to select. Okay. So normally it can be found numerically that the maximum margin on the communication delay in this particular case has been given by this particular value, let's say 0.3490. So now we go for the heterogeneous delay simulation. So let's say I am having 4 agents in my CPS, and this is the teacher trajectory that is given by 1 plus t plus I. So this is the initial values of the position and velocity of the agents. These are the input delays, and these are the communication delays. So we want to have a comparison like that, which estimator structure is giving the performance better or worse. So for that reason, I am taking identical set of design parameters for both the design. So this controller gains how can design based on the thing. Like here, from here you can find out what should be the controller gains, and from this stability condition you can find out what should be the estimated gains. So satisfying that stability criteria, we can choose this particular values. So normal basic thumb rule is that don't go for values which are very marginal. I mean, let's say on the verge of instability, if you are taking some estimated gain or control gain, in that particular what will you see that the system is stable, but it will have large value of oscillation. So you can take as a thumb rule, like let's say in between, let's say 0 and that particular threshold. And for agent 1, which has the information of the descent trajectory, we just select the gains like this, gamma 1p and gamma 1b. So here xi is the position and vi is the velocity. So you can see here that the agents finally follow the desired trajectory. The red color one is the desired trajectory. This is for the estimator of the design 1, and this is based on the estimator design 2. So similarly, velocity profile can also have been plotted here, and you can see, of course, both the design when it satisfies the stability criteria, tracking is possible. Now it is, of course, bounded tracking. You can see from here also that that red colored one is the XT dot. So there is little bit gap between the agent states, agent's velocity states, and XT dot. Similarly, that is true for the position also. But our objective is that I have to ensure bounded tracking. So let's say one vehicle is moving, that is the reference vehicle. and the other vehicles will try to follow that particular vehicle with some, let's say, deviation. So it should not be outbound mode. So that means it should not happen that there should not be continuity gap like that one vehicle is moving towards some different direction or something. It should follow that particular direction. So based on this, we can have this both the design one estimator and design two estimator, and ensuring that my system is having bounded traffic. So let's see that if we compare with some other works which consider only controller based architecture, so there is no presence of estimator. So in general, if you have this input delays in your system and communication delays in your system, you can directly take that into your controller signal. Like you have to design some UT. Now that UT will handle both the input delays and the communication delays. So that is also possible, and of course that is solvable. You will come up with a big LMI, and based on the feasibility of that particular LMI, you can say, okay, my system is stable. It can handle this much of input delays, this much of communication delays. That is correct. But again, the problem with those kind of control architecture is that mixing of the delays are present in the system. That is one thing. And in case of CPS, another big problem with that kind of controller architecture is that the size of the LMI will be very large. Let's say you are having, let's say 20 number of agents. So, and let's say you are having double integrated dynamics. Then the size of the LMI will be huge because the LMI of, because this time it is not the LMI of individual agent, rather it is the LMIs of the complete system. So whenever I am telling complete system, that means that system consider 20 number of agents together. So you have to find out the state space representation of 20 number of agents, that complete matrix will come in the system. So that total system will have been ensured stability based on the feasibility of LMI. So if you go here, what we have done for the LMI in this particular case. So yeah, here if you go, you can see here the LMI I am doing for the tracking controller gains only. So for the tracking controller gains, I am having that system to be not to be the complete system. It's the individual agents only. So let's say I am having this double integrated agents, that means it's a second order system. So I don't have to go account for the n number of agents, 20 number of agents. So that the advantage of this is that I don't have to deal with the big, large LMIs. So solving our large LMIs is actually problematic. I mean, finding the physical solution, because at the end of the day, you have to find a physical solution, and there exist conservative results also. So more practices are there how to found this particular Newton-Krasowski function or the Rajanikhan theorem, such that you can reduce the conservatism in your system. So I can design some kind of Newton-Krasowski, but it is very much conservative. So of course, if the feasible solution of that particular inequality exists, you will have the solution. But what is the guarantee that the feasibility of that matrix will be satisfied? So that's how the conservative will come in your system. So it is wise choice to make the LMIs of smaller size, and mostly we can get a feasible solution. So there is no guarantee. So based on the system's architecture, these LMIs will have the different kind of delay margin in your system. So yeah. So we are here. So the stability condition is obtained through a feasible solution of a large LMI that I have told, which involves the coupling between input and communication. And you can see in the simulation here. So we have, let's say, this is the tracking position error, and this is the tracking velocity error. Okay. So this is if the input delays and communication delays interact with each other, then you will get this kind of solution. Of course, in this particular case also, you can ensure boundary tracking. And this is for the velocity profile. And this is based on the estimator based controller architecture. Of course, we go for the boundary tracking. You can see here in terms of the error difference, this graph is outperforming the past one, because in this particular case we have actually segregated the effect of delays. So what could be the possible extension? Like in this particular case, let's see, I have considered constant delays. Now the delays can be time varying in nature. So in that particular case, we have put up Krasovsky functional. Whatever we have designed for, we have to modify that, because that time not only the values of the delays, but yeah. So not only is the value of the delays, but the, what should be the upper bound of the tau by dot t, that will also be significant. So based on that, we have to modify the Lyapunov-Krasovsky functional, and we have to go for the stability analysis of that. So several criteria exist there, Jensen's inequality, so Wrangler's equality. So there are several methods by which you can solve those particular LMIs, and research is going on in this particular field also. And one more thing is that in this, so from where we have started, so we actually discuss more only on this distributed control. Now, whenever you have to implement that on a real-time system, that time this real-time control will come into your system, and you have to take the precaution of the rigid body dynamics also. So you have to go for the collision avoidance protocol such that none of the agents interact with each other, none of the agents collide with each other. So those kind of systems will be there. So the primary is the, let's say, low level control. After that, this kind of distributed control will come into the system. Wireless sensor networks altogether will have a complex scenario. So that's why whenever you are calling that a CPS, cyber physical system, we have to consider all the three aspects, that is the computing design space, control design space, and communication design space. So those who are interested in the communication part also, they have to consider what is that packet loss and everything that should be plugged into your system. So you will see that whenever you are actually working in this complex system, so many aspects are there in the system. Of course, trade-off will be there. So here in today's lecture, we have talked about only one aspect, that is the time delays in your system. So many aspects will be there in your system. So sometimes you will have the unmodeled dynamics in your system. So how to get rid of that? So that area, that's why is ever spending. So yeah, that's all. So if you have any doubt, please ask me. So if you have any doubt, you can ask me now, or my email ID is saradipday@mnnit.ac.in. You can mail me. I will be happy to answer your queries. Thank you.
Dr. Saradeep, thank you.
Thank you, sir.
And on behalf of the participant, I request you to please share your PPT with us so that the same can be shared with the participants.
Definitely, we'll share the PPT, and I think they will get it by today's evening, so that they can prepare for tomorrow's quiz, which is actually essential for them to get the certificates.
Yes. So I believe all the sessions of day 4 have been concluded successfully. So if there are no further queries from the participants end, then we can conclude the sessions over here. And tomorrow the session will start at 14 hours IST. So I request the participants to join before time. And I repeat again, although the Dr. Day has mentioned several times in the afternoon sessions that attending the quiz is compulsory. So I request all again to present and participate in the quiz test, because that evaluation will help us to issuing the certificate of this 1 week GYAN course. So with this, we are closing this meeting over here, and thank